In our last several videos, we took a look at limits. In this video, we are going to turn our attention to the idea of continuity, right? And so we are going to formally define what it means for a function to be continuous at a point, and then we will talk about what it means for it to be continuous on a set, and for it to be a continuous function. Right, but let's first take a look at what it means to be continuous at a point. So let f be this function, and c is some value in the domain. We say that f is continuous at c if for every epsilon greater than 0, there exists a delta greater than 0, such that the distance between f of x and f of c is less than epsilon whenever the distance between x and c is less than delta, and c is an element of the domain. Right? Some of you may say, this feels a whole lot like the definition for the limit. And I would say, that's correct. It really is a whole lot like the definition for a limit. The difference here, the major maybe two components of difference, is right here, this is f of c instead of L, right? So this is specifically the function value at c, right? So we could have, when we were looking at a limit, you could imagine having a function that is discontinuous at c, that has like a hole there, but is defined way up or way below that previous value, way up or way below the value of L that it looks like is the limit, right? We also have here whenever the absolute value of x minus c is less than delta, right? So when we looked at limit, we said that this was a non-zero value. So for limit, we said we were looking at this. But for continuity, we are not saying that, because we are saying at the point C, we still need to satisfy this as well, because that at the point C, we're going to be equal to the limit itself, right? So it does have all those ideas from limits, but it's going to be a little bit stronger. All right, so we say that f is continuous at c if for every epsilon greater than 0, there exists a delta greater than 0, such that whenever the distance between f of x and f of c is less than epsilon, so that is true whenever the distance between x and c is less than delta and x is in the domain, right? And so we have for our y values for those that vertical axis, we can say we're going f of c plus epsilon and f of c minus epsilon, right? So we're going to be looking at, we want to ensure that we are within that vertical window. We don't have to get all of that vertical window, but we want to say what restrictions do we have to place on a horizontal window in order to ensure that we are in that vertical window. All right, so if we choose delta in this way for this particular function, so this is c plus delta, and then we're going to subtract that same value of delta, c minus delta. Then for this function, we can say whenever we are within delta units of c, whenever x minus c is less than delta, then this is going to imply that we're going to actually have to be in this more restrictive area. So we're in this more restricted area on the horizontal or on the vertical axis. So our values of f of c, our values of f of x, are, no matter what, going to be less than epsilon units away from f of c, right? So at worst, we go up here, right? So it's kind of right here, just below that value. And then if we were to be delta units below c, then kind of like our worst case scenario is that we're not even epsilon units below f of c on this particular graph. Right? We could also think about these in terms of neighborhoods. So in terms of neighborhoods, right, we can say we have this epsilon neighborhood about C, right? So we could say this is not C, about f of C. You have this epsilon neighborhood about f of C, and we want to ensure that we're going to be in that epsilon neighborhood. Whenever our function value, our values of x are within an epsilon neighborhood of C, or a delta neighborhood of C, I'm sorry. So whenever, so that pink stuff, we can imagine that's a delta neighborhood of C. So whenever we're in this delta neighborhood of C, that's going to ensure that the outputs are going to live in this epsilon neighborhood of f of C. Right? And so that's continuity. If f is continuous at each point in a subset S of D, then S is continuous on S. That should not say S, that should say then F so then we have F is continuous on S. And we could also say things like, if it's continuous on its entire domain, then f is actually a continuous function. If we have, so what are some properties of continuity, or what are some other things we think about? With continuity, we have, if f is this function and c is a point in the domain, the following things are equivalent. So whenever we say something like f is continuous at c, that is exactly equivalent to saying if we have some sequence in the domain D that converges to C, then the limit of f of x sub n is also going to be f of c, right? So that the function evaluated at each of those terms in the sequence should converge to f of c. And it's also equivalent to saying for every neighborhood V of f of c, there exists a neighborhood U of c such that f of u intersect D is a subset of V, right? And so that's really kind of what we were looking at here, over here on the second piece, right? Whenever we were within here, wherever we were in this neighborhood, we were guaranteed to be at least within a subset. So we might not have picked up the whole neighborhood. The stuff that we had output here was just a subset of that neighborhood, that epsilon neighborhood here. Right? And so that's what that third item says. Furthermore, we can say a little bit more. If we happen to have something that is, if C is an accumulation point of D, then the above items are also equivalent to this one other thing. F has a limit at C, and the limit of f at C is equal to f of C. We can note the one other thing. If C is an isolated point of D, then we say that f is continuous at that point. All right, so that is our definition of continuous. In our next video, we are going to take a look at some examples. We'll talk to you guys later.